Ancient and prehistoric mathematics. The earliest evidence of mathematical thinking comes from tally marks on bones dating back to 35,000 BCE. Around 3000 BCE, the Sumerians in Mesopotamia developed one of the first sophisticated number systems using a base 60 system, which is why we still have 60 seconds in a minute and 360 degrees in a circle today. The Babylonians built on this and were able to solve quadratic equations and had an approximation of pi as early as 1800 BCE. The Egyptians developed their own number system based on hieroglyphics and were able to perform complex calculations needed for construction, taxation, and astronomy. The Rhind mathematical papyrus from around 1650 BCE shows that Egyptians could calculate areas, volumes, and work with fractions. They used this mathematics to build the pyramids with incredible precision. Greek mathematics era. Starting around 600 BCE, Greek mathematicians shifted focus from how to why, demanding rigorous proofs for mathematical statements. Thales of Miletus is credited as one of the first to use deductive reasoning in geometry around 580 BCE, proving theorems rather than just observing patterns. But the most influential figure was Pythagoras, who founded a school around 530 BCE where mathematics was seen as the key to understanding the universe. The Pythagorean theorem, which states that in a right triangle the square of the hypotenuse equals the sum of squares of the other two sides, became one of the most important theorems in all of mathematics. The Pythagoreans also discovered irrational numbers, though this discovery troubled them so much that legend says they tried to keep it secret. Euclid changed mathematics forever around 300 BCE with his book Elements, which contained 465 propositions covering geometry, number theory, and algebra. Archimedes, working around 250 BCE, made groundbreaking contributions to geometry and calculus-like thinking, calculating areas and volumes using the method of exhaustion. He also approximated pi to be between 3.1408 and 3.1429. Islamic Golden Age. The Islamic Golden Age was when mathematics flourished in the Islamic world from roughly 750 CE to 1250 CE, preserving Greek knowledge while making revolutionary advances of their own. The most important figure of this era was Muhammad ibn Musa al-Khwarizmi, who worked in Baghdad around 820 CE and wrote the book Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which gave us the word algebra. Al-Khwarizmi developed systematic methods for solving linear and quadratic equations, completely changing how mathematics was done. His name also gave us the word algorithm. During this era, Islamic mathematicians adopted and spread the Hindu-Arabic numeral system, which included the revolutionary concept of zero as a number. This numeral system was far superior to Roman numerals and made complex calculations much easier. Omar Khayyam, working around 1070 CE, made significant advances in solving cubic equations geometrically and contributed to the development of binomial coefficients. Al-Biruni calculated the Earth's radius to within 1% of the actual value using trigonometry around 1025 CE. Islamic mathematicians also made major advances in trigonometry, developing sine, cosine, and tangent functions that were essential for astronomy and navigation. Renaissance mathematics. The Renaissance mathematics period, spanning roughly from 1400 to 1600 CE, saw mathematics re-emerge in Europe with new symbolic notation and solutions to ancient problems. Leonardo Fibonacci introduced Hindu-Arabic numerals to Europe with his 1202 book, Liber Abaci. Fibonacci also introduced the famous Fibonacci sequence, where each number is the sum of the two preceding ones, which appears throughout nature and art. In 1545, Girolamo Cardano published Ars Magna, which contained solutions to cubic and quartic equations developed by him, Niccolò Tartaglia, and Scipione del Ferro. This work also introduced complex numbers, though mathematicians wouldn't fully understand them for another 200 years. François Viet, working in the late 1500s, revolutionized algebra by introducing the systematic use of letters to represent unknown quantities and parameters. The calculus era. The calculus era was when mathematics gained the tools to analyze change, motion, and infinity, fundamentally transforming both mathematics and physics. In the 1660s and 1670s, Isaac Newton and Gottfried Wilhelm Leibniz independently developed calculus, though their approaches differed significantly. Newton developed his method of fluxions to solve problems in physics, particularly the motion of planets and objects under gravity. He used calculus to prove that Kepler's laws of planetary motion followed from his law of universal gravitation, unifying terrestrial and celestial mechanics. Leibniz, working independently, developed a more systematic and notation-based approach to calculus between 1674 and 1686. His notation using for derivatives and the integral sign proved far superior to Newton's and is still the standard today. The bitter priority dispute between Newton and Leibniz split the mathematical community for decades, with British mathematicians loyal to Newton falling behind their continental counterparts who used Leibniz's superior notation. Calculus allowed mathematicians to solve problems that were previously impossible, like finding tangent lines to curves, calculating areas under curves, and determining rates of change. The fundamental theorem of calculus, which connects differentiation and integration as inverse operations, is considered one of the most important discoveries in mathematics. With calculus, scientists could now mathematically describe motion, acceleration, optimization, and any process involving continuous change. This transformed physics, engineering, economics, and virtually every quantitative science. Age of Enlightenment mathematics. The Age of Enlightenment mathematics, spanning roughly 1700 to 1800, was when mathematicians put calculus on rigorous foundations while expanding into new areas like number theory and probability. Leonhard Euler dominated this era like no other mathematician, making fundamental contributions to virtually every area of mathematics during his career from 1727 to 1783. Euler introduced much of modern mathematical notation, including e for the natural logarithm base, for the imaginary unit, pi for pi, and f of x for function notation. He proved that e to the power of e times pi equals -1, known as Euler's identity, which beautifully connects 5 fundamental mathematical constants and is considered the most remarkable formula in mathematics. Euler published over 800 papers and books, contributing to calculus, graph theory, topology, number theory, and applied mathematics. Pierre de Fermat, working earlier in the 1600s but influential throughout this period, made major advances in number theory and wrote his famous last theorem in the margin of a book around 1637. Fermat's last theorem stated that no 3 positive integers, a, b, and c, can satisfy the equation a to the nth power plus b to the nth power equals c to the nth power for any integer value of n greater than 2. This seemingly simple statement wouldn't be proven for 358 years, becoming mathematics' most famous unsolved problem. The Bernoulli family, including Jacob and Johann Bernoulli, made significant contributions to calculus and probability theory. Jacob Bernoulli's work on probability, published posthumously in 1713, established the law of large numbers. This era also saw Joseph Louis Lagrange develop analytical mechanics, reformulating Newtonian mechanics using calculus of variations. 19th century rigor era. The 19th century rigor era was defined by mathematicians questioning the foundations of mathematics itself and discovering that multiple consistent geometries could exist. Carl Friedrich Gauss, often called the Prince of Mathematicians, made groundbreaking contributions to number theory, statistics, geometry, and physics between 1795 and 1855. Gauss developed non-Euclidean geometry independently but didn't publish it, fearing controversy over challenging Euclid's 2,000-year-old axioms. Nikolai Lobachevsky and Janos Bolyai published their own versions of non-Euclidean geometry in the 1830s, proving that Euclid's parallel postulate wasn't necessarily true and that consistent geometries could be built on different assumptions. Bernhard Riemann extended this further in his 1854 lecture, developing Riemannian geometry, which would later become essential for Einstein's general relativity. Georg Cantor revolutionized mathematics in the 1870s and 1880s by developing set theory and rigorously studying infinity itself. Cantor proved that some infinities are larger than others, showing that the infinity of real numbers is strictly greater than the infinity of natural numbers. Évariste Galois, dying in a duel at age 20 in 1832, created group theory and proved which polynomial equations could be solved by radicals, work so advanced it wasn't fully appreciated for decades. Augustin Louis Cauchy provided rigorous definitions for limits, continuity, and convergence, putting calculus on solid logical ground for the first time. Karl Weierstrass found continuous functions that were nowhere differentiable, challenging intuitions about smoothness. Early 20th century crisis and foundation era. The early 20th century crisis and foundation era was when mathematicians discovered paradoxes in the foundations of mathematics and debated what mathematics truly was. In 1900, David Hilbert presented 23 unsolved problems to the International Congress of Mathematicians, providing a roadmap for 20th century mathematics. Many of these problems, like the Riemann hypothesis, remain unsolved to this day and are considered among mathematics' most important questions. In 1901, Bertrand Russell discovered a paradox in set theory. If R is the set of all sets that don't contain themselves, does R contain itself? Either answer leads to contradiction. Hilbert proposed a program to formalize all of mathematics and prove it was consistent and complete, meaning every true statement could be proven. But in 1931, Kurt Gödel shattered this dream with his incompleteness theorems, proving that any consistent formal system powerful enough to describe arithmetic must contain true statements that cannot be proven within that system. L. E. J. Brouwer developed intuitionism, arguing that mathematics is a mental construction and only constructive proofs should be accepted, rejecting the law of excluded middle. The Bourbaki group, formed in the 1930s, attempted to rebuild all mathematics on rigorous set theoretic foundations, publishing influential textbooks emphasizing abstraction and formalism. Despite the foundational crisis, mathematics continued advancing rapidly in topology, abstract algebra, and analysis. Computer mathematics era. The computer mathematics era, beginning in the 1940s and accelerating through the 1990s, was when electronic computers transformed how mathematics was done and what problems could be solved. Alan Turing, in his 1936 paper Before Computers Even Existed, defined the theoretical limits of computation with his concept of a Turing machine and proved that some problems are fundamentally unsolvable by any algorithm. John von Neumann developed the architecture for modern computers and pioneered numerical methods for simulating complex systems like weather and nuclear reaction. In 1976, Kenneth Appel and Wolfgang Haken proved the four-color theorem, which states that any map can be colored with just four colors, so no adjacent regions share a color. But their proof required checking thousands of cases by computer. This was the first major theorem proved with computer assistant, sparking debate about whether such proofs were truly valid since no human could verify every step. The RSA encryption algorithm, developed in 1977 by Rivest, Shamir, and Adelman, used number theory to create secure communication. Andrew Wiles proved Fermat's last theorem in 1995 after 7 years of isolated work, finally solving the 358-year-old problem using advanced techniques from algebraic geometry and number theory. Modern mathematics era. The modern era has been defined by two things so far: technology-assisted mathematics and massive collaborative efforts on century-old problems. Machine learning and artificial intelligence are now being used to discover patterns, suggest conjectures, and even assist in proving theorems, with DeepMind's alpha geometry solving international mathematical Olympiad geometry problems in 2024 at near medal level. In 2003, Grigori Perelman proved the Poincaré conjecture, one of the 7 Millennium Prize problems, using Ricci flow techniques he developed over 2 to 2003 papers posted online. The conjecture states that any closed three-dimensional manifold that is simply connected is homeomorphic to a three-sphere, and it had remained unsolved for nearly a century. Perelman famously declined both the Fields Medal and the $1 million Millennium Prize, saying the prize was irrelevant compared to the mathematics itself. Shinichi Mochizuki claimed a proof of the ABC conjecture in 2012, posting over 500 pages of dense work introducing inter-universal Teichmuller theory. But the mathematical community is still debating whether the proof is valid over a decade later. The Polymath project, started in 2009, enables mathematicians worldwide to collaborate on problems through online platforms, successfully solving problems through massive crowdsourced efforts. In 2016, a formal proof of the Kepler conjecture about sphere packing was verified by computer, requiring both human mathematical insight and computational verification.